Okay, so basically these concepts in physics are really easy to get mixed up on, and I got messed up on them when I was starting out as well, so it's very common. But there's two basic things that you have to remember with these, and that is the slope of the graphs and the area of the graphs. So when you're going from the position to velocity to acceleration, what's changing? So when you're looking at the position graph, on the x-axis you have the time, and on the y-axis you have the position. So the units is seconds, meters. And we know that the slope is y over x. So the slope is in meters per second. But what's the units for velocity? Meters per second. So the slope of the position graph is the velocity. The slope of the velocity graph, so if you look at the velocity graph, you got meters per second. Sorry, you have seconds, time, and then you have the velocity. So the slope is going to be meters per second over seconds, or meters per second squared. And that is your units for acceleration. So that is going to be something important to remember to tell you, what exactly the relationship between these is. So the position graph tells you where you are, and then the slope of slope of that graph tells you how fast you're changing where you are, right? And that's your velocity. The slope of the velocity graph tells you how fast you're changing, how fast you're going. And so the rate of change of your speed of your velocity is your acceleration. So basically, let's look at some, things. So if your slope for your position graph, so this is like how to interpret your position graph. If you have if you have a positive constant slope, right? So if it's, a diagonal line and it's positive, going up, straight line slanted up, you're moving at a constant positive velocity. And that means that your velocity graph will be a flat horizontal line above the x-axis. So again, let's look. You are constantly moving in your position graph. So the position and where you are is changing at a constant rate, right? But that means that our velocity, which is the slope of our position graph, isn't changing. So that means that when we look at the velocity graph for our position graph, we're looking at the slope. We see that the slope is constant. That means it's going to be a straight line. It's not changing at all. So, okay, if you have a negative constant slope, so if it's a straight line slanted downwards, that means that you're moving at a constant negative velocity, and your velocity graph will be a flat horizontal line below the x-axis. And if you look at this, positive, positive constant slope on your position graph is going to give you a straight line in the above the x-axis for your velocity graph. And then what's our acceleration graph going to look like? Well, we know that our acceleration graph is the change of our velocity. But if, from our first graph, we know that our velocity is going to be constant. That's why our velocity graph, it's not changing, it's just positive. But because it's constant, for our acceleration graph, our acceleration is 0 because there's no change in our velocity. So if you have a 0 slope on your position graph, so it's just a straight line for your position, you're not moving, which means your velocity is 0. And if your velocity is 0, so your velocity graph will be a flat line right on the x-axis, 0, then your acceleration graph is also going to be 0. So then what you were saying with like top and bottom on a velocity graph, it's a lot simpler than it sounds. So an object is at the top or bottom of its motion when it momentarily stops to change directions. So think about throwing a ball in the air, right? So if I'm throwing a ball in the air, it's going to peak and then come back down. When it peaks, for a moment, its velocity is going to be 0. because that peak is going to change its direction when the ball is going up and it gets to its peak and it comes back down. At that point to where it changes direction, your velocity is 0. Because at that point, your, like, for a moment, you're not moving, right? And then you start moving back in the other direction. For example, if I'm running this way and I turn around to go the other way, for a moment, I've stopped, turned around, and now I'm going that way. So for that moment, your velocity is 0. So if you're looking at the graph, the velocity time graph, this turning point happens when the object's velocity is 0. So if you're looking at a straight line, I'm trying to picture the graph for you. Whenever the velocity crosses the horizontal axis, so at that time it's 0, that is when you have stopped, or its direction is about to change. So then you're looking at, so the next question will be quantitative instead of it being qualitative. So to go from a velocity graph back to the position graph, the key idea here is area. And so this is why I was asking whether or not this is a calculus-based course or a algebra-based course, because if you have calculus, going from position to velocity to acceleration graph, you're doing a derivative and a derivative. Going from acceleration to velocity to position, going the other way, it's just an integral. But in algebra, or in algebraic terms, you're basically looking at the area under the slope. So for example, the change in position, also called the displacement, is the area under the velocity versus time graph. So how do you find the plot of a quantitative position graph step by step? So for example, finding your starting point, the problem usually tells you the initial position, like x is equals to 0 meters at t equals 0 seconds. If not, you can assume it starts at the origin, right? So then break the velocity graph into smaller shapes. So look for rectangles or triangles that you can visually see. And typically in an algebra-based course, you can, like, the shape underneath, it's like an exact shape. So for example, calculating the area of each shape. So the area of the triangle is 1/2 base times height. The area of rectangle is the base times the height. And then crucially, the area above the t-axis is a positive displacement. The area below is a negative displacement. So then you're going to plot the position points. So your position at the end of an interval is your position at the start of the interval plus the area you just calculated. So you have your starting position, you have this area that you calculated. So if you add those together, that is where your position is then at. That makes sense. So then you're connecting the dots. So if the velocity was flat, a constant straight line, your position graph will be a straight slope, right? If the velocity was a straight sloped line, constant acceleration, then your position graph will be a curve, if that makes sense. So you have, if you have a straight line for your velocity, if you look at the starting position and then the area underneath that will tell you that your brain, come on. That will tell you that your position graph is going to be a constant, like, horizontal line. And so basically, I want to tie this to, very simple calculus, but, and this helps me. So if your position graph is a constant line, right? It's a diagonal. Then your velocity is going to be here, just a flat line. And then your position graph is going to be at 0. If your if your position is now a parabola, right? You know, parabola, your velocity is then going to be a diagonal, and then your acceleration is going to be flat. And so basically that is the going from position velocity to acceleration. And then the reverse is if you have your acceleration at 0. It's kind of hard to start from your acceleration. So like if you have your velocity, right, and your velocity is positive and it's a straight line, you can immediately think, okay, my position graph will be a constant slope, because my velocity graph, its line is constant. The entire function is constant, which means that the slope of my position graph should be constant, which means it's diagonal. Now, whether it's diagonal down or diagonal up, that is going to be from whether your velocity line is a straight this way, or a straight positive, or a straight negative. And you know it's positive if it's above the x-axis. You know it's negative if it's below the x-axis. So that's that concept. And then, for example, if your velocity is at a constant slope, which means you have constant acceleration, then that you have to then say, okay, my position graph, if my my position graph, if my velocity graph is a constant, if my velocity graph has a constant slope, then my position graph will have a like a parabola. And then like the algebraic explanation of that is like with the whole area thing, but I'm pretty sure you can get away with just knowing that if your velocity is a diagonal positive, your position is going to be a positive parabola. If your velocity is a negative diagonal, then your velocity is going to be a negative parabola. Sorry, your position is going to be a negative parabola. And then if your velocity is constant, then your constant positive or constant negative, then your position is either going to be constant slope positive or constant slope negative. And then if your velocity graph is 0, that means that your position graph is going to be a straight line. And where do you know where to put it? That is fully based off of what position you start at. So for example, if you start at 5 meters at 0 seconds, you're going to start at that, you're going to start your line at 5, 0, right? Or technically it'd be 0, 5, the coordinate. And then it's going to be a straight line because you're not moving because you have 0 velocity. I hope that makes sense. Again, like I can explain the calculus version of it a lot better or a lot simpler, but basically I can send you videos of like a better algebraic explanation, but I hope that helps.